So today we have Yilong Zhang from Purdue University, who is going to talk about periods of cubic surfaces. So please, Yilong.
Thank you for the invitations. And so today I'm going to give a talk, which is sort of part of work is from my thesis. Part of work is joint work with Marquand, and so I think I will just my plan is an introduction, and starting from some examples, and so cubic curve, and then talk about cubic surface, and then after talking about the cubic surface, we are going to talk about what is the meaning of these periods, and what is a moduli space, and so there is a modular map, like by taking hyperplane sections, and that's our main topic. Which is to consider hyperplane section of cubic threefolds, and we want to really consider that family of cubic surface and how this deform in the moduli. Okay, so maybe so first of all is it is a cubic curve, where we know that for cubic curve, and it is really just a torus, and so how to make sense the periods? So well, we have a integral homology, gamma and delta. So H1 is let's say this is a curve. It is Z gamma and V delta. Well, and also there is a holomorphic one form. So we can integrate this one form along gamma, and also along this delta. But this is like there's a scaling for this holomorphic one form. To eliminate that scaling, we divided that. So this is called, so this is a period. So this sort of tells us that how this is it tells us the Hodge structure of this Yilong curve. So this period, how tells us Hodge structure. So sort of we have complex coefficients, which is given by integral coefficients cohomology. We tensor C, and this decomposed as a holomorphic part and the anti-holomorphic part. And this omega lives in here. But then here we have a basis like a C delta and C gamma. And so this period is telling us, writing down this 1,0 part in terms of the integral basis. So this is tell us where the Hodge structure is. And this is maybe the simplest example of the periods. So then we can talk about moduli space. in different aspects, and there are various ways to study it. But one way is to use the periods, which tau lives in. So this tau is leaving this upper half plane, but up to change of basis, and we have a SL2Z. So so it turns out that this is like a C. Topologically is a projected P1 by removing one point. In a sense that it admits. So this is a Riemann surface, and it admits a compactification, which by adding a point, and turns out that this is exactly CP1. So this is we can say this is so this add one point. So this added one point we can think about as degenerating the cubic curve into a nodal cubic curve. So the boundary point of this compactification SL2Z corresponds to a nodal curve. And if we think about this nodal curve like arising in a family, and it's really, in fact, captured by the periods. Oops, this is the ordinodal. So let's say this is a smooth curve with this delta and also gamma, and this degenerates into there is only one gamma. The delta is already vanishes. So delta is a loop here, but it's homologous to this node, so it doesn't exist. So we can think about our period. What is going on with periods? So we say that we have a one form integral over gamma over delta. And you can think about even this delta like a vanishes, and this just as a one topological one chain still stays here, and this holomorphic one form it still makes sense to define its integral. So this is still fine. So you can think about this. We have a Fresnel curve and this tau, and that all varies in the parameter, and from here and. So we let t goes to infinity, and this is something stays finite. So this is a finite. However, this holomorphic one form it is going to have a pole here, and which means that if you really integrate along gamma, and this is going to be something. So let's say I'm just writing this way, but this is so this is infinite. So really, the whole period is approaching to the infinite, and with logarithmic growth, so sort of like by looking at the period and it's monodromy, and you can really understand the geometry of this nodal curve and also the degeneration. And this is a sort of classical theory of understanding this it'll be curved, and also similar to other genus curve. Right. So, okay, so probably the topics of this talk is going to not really focus on the periods, but focus on the other way to characterize moduli space using GIT. So, for example, the other or another way to define moduli is using the GIT quotient. So where you consider the space of so let's say Pn, and this is a space of all cubic equations, Planck cubic equations, and by changing of GLN action, this is another way to define this moduli space. So why do I introduce this? Because actually you can say you can ask so what happens to Causpedal curve? So what happens to Causpedal curve in as an example? We can consider this family. So y squared into x cubed plus t. Yeah, this family. And so this family is like when t equals to 0, you have Causpedal curve, and when t is non-zero, you have smooth curve. So this is t equals 0. So there are two ways to understand it. You can still talk about the periods of this family, right? So because nearby is smooth, and you can see how the periods goes. But the thing is that this is an isotrivial. So periods probably is constant periods. And this monotony is actually a finite monotony. So you would say that so how do I deal with this Causpedal curves in the moduli? And so in the sense there's a GIT, a moduli space, and there is a way, as long as you have a family of like say we call it stable objects, and approaching something non-stable, and there is a way called semi-stable reduction, which after some base change, and we can do some directional change, and to replace this central fiber to some stable fiber. So this is a idea is such a so this is a parameterized by this t, and you can think about you have a map from the puncture disk map to this moduli space. But the GIT is like a projective, so it's compact. If you have some like a curve map to some compact space, you can always close up. And by closing up in the so you are really thinking about this replacing this bad fiber by some good fiber in the GIT moduli space. So this is obtain good fiber at t equals 0. So this is so geometrically, so this this extension comes from a so-called semi-stable reduction. So which just so in other words, up to taking a finite base change, so one can blow up and blow down. Meaning that you can prefer some directional change on the total space after your base change, and so that you modify your new family and to make your central fiber, which is stable, to make central fiber stable or semi-stable. I should say semi-stable. So here for semi-stable, maybe I haven't really say anything about semi-stable, but really this just is equivalent to say that curves with this nodal singularity. So we are improving the cascadal singularities to something which nodal, and this is a this is like a semi-stable reduction for curves. So in this case, it's actually a 6-to-1 cover. In this case, so phase change it is 6-to-1 cover. And so this example I learned from Joe Harris' book and Ian Morrison, their book from moduli of curve, and they have a nice example how to blow up and blow down, which is quite geometric and right. So I should ask, is there any questions?
So after this this modification for this example, it is still isotrivial, no? I think.
It is still isotrivial. The nearby fiber doesn't change. It's still isotrivial, and the central fiber and is I think it's even trivial. So after your base change, there is no monotony, and the central the new fiber you obtain is exactly the nearby.
Yeah. In this case, but it's just a product with the disk there. Just one.
Yeah. That's right. In this case, is we just obtain a product. Right. So okay, so maybe this is the end of the introduction part, and we will begin to talk about stories in cubic surface. So we basically increase one-dimensional up. So to increase one-dimensional up, we have to think about two issues. One issue is what is a Hodge theory for surface, and the other is that what does a stable or semi-stable mean in surfaces? So this for I think even for surface it can be subtle. Yeah. So because I learned from some directional geometer who told me that basically for curve and the GIT stable, semi-stable is under directional geometry. This concept are the same, but for higher dimension, might have it may not really be the same. So now let's talk about cubic surfaces. So cubic surface is basically S is a blow up of P2 at 6 points. Of course, in general position. So, so we have a picture of this. Right. So. And so then it's related to this title. So what is the meaning of the periods of this? Because it's arising as blow up of P2, it's a rational surface. It is rational, and all H2 SE. I mean, if we tensor with so this is a 7 copy, and generated by this pullback of hyperplane and those exceptional divisors. The Hodge decomposition is there is no 2,0 and 0,2 part, and everything is in this 1,1. So its Hodge structure is not interesting. So there is no way to say, like you vary your surface, your Hodge structure varies. It doesn't matter. If you look at the H1, is of course is 0, so it's not interesting either. However, there is a very interesting point of view by Allock, Carlson, and Toledo. Is that one can consider like a cyclic cover of P3 along this cubic surface. So if this cubic surface is given by x0 up to x3, so this cyclic cover is just introducing a new variable x4 is equal to f x0 up to x3. And so this is defining equations in P4 in variable x0 through x4, and which is a homogeneous. So this is a homogeneous of degree 3. This is also homogeneous of degree 3, so which is a cubic threefold. If f is singular, and this is also singular, of course. So if s is smooth, this is also smooth, of course. And but for cubic threefold, and its middle dimension has an interesting Hodge theory. So so then the cubic threefold has non-trivial H3 as Hodge structure. So in fact, there is a Torelli theorem which says that the Hodge structure of cubic threefold uniquely determines cubic threefold. There's a Torelli theorem saying Hodge structure H3 determines cubic threefold. So what Allock, Carlson, and Toledo considered was really to study the middle cohomology of the cyclic cover, and also at the same time keep track of the group action. So really study this H3 as a representation of this cyclic action, and there you can extract some like a smaller Hodge structure out of this Hodge structure, but that Hodge structure is used to define the moduli. So this defines. So this defines an analytic moduli space of cubic surface, actually as a ball quotient. So it is a four-dimensional ball quotient by some arithmetic subgroup. Which is an example of period domain. And turns out that there is still a complication of this Hodge theoretical modular space, and which is called Bailey-Gorel complication. So in this case, it's sort of very similar to the recurve case. You just add one point in the infinity. So in this case, it's also adding a 1 point. So this is basically it only adds 1 point.
Hey, Yilong, sorry. So you mentioned that you didn't take the full Hodge structure of the cubic threefold for defining the moduli?
Yeah. So there are some details in between. So it's sort of not only consider this H3 of the cubic threefold, but consider the group actions on the X3. And under this group action, you can extract a four-dimensional subspace out of this X3. And that is sort of you can think about it as another version of Hodge decomposition with group action, and they can associate to like a subspace of this, and which uniquely parameterize the cubic surface.
But this group action is coming from the covering, or?
Here, so its group action is from.
I see. This the cyclic covering.
This is cyclic cover. Sorry, yeah, I should say that.
Yeah. Okay. Thank you.
Yeah, no problem. Are there any other questions? Okay, so by the way, the Berville has a nice survey article on this subject, and I learned from that paper actually. So he gave a good description of how is the construction of this like a subspace of H3 is. So really, we'll have to use the group action and consider a new intersection pairing. So this is a still Another way, or just say, okay, I'll say GIT approach. So GIT approach is something similar. We consider the moduli space of all the cubic surface as like this 19 is a space of all the cubic equations in P3, and then it's changed by this project PGLN action. And from here, it is so this is four-dimensional projective variety with only quotient singularity. So in fact, this moduli space is a really projective space 1, 2, 3, 4, 5, and that's a different description of this moduli space. And also, I don't know which name to cite, but this is this GIT moduli space and the analytic moduli space of Billy-Brown complication, they actually coincide. It's the same as the Hilbert curve case. When I say coincide, what I mean is that this is some analytic space, and this is some algebraic variety. So you can, so there is a biholomorphism between the two, and so in other words, you can give a algebraic structure on this analytic space. So this is actually biholomorphic. So this is a two-way of characterizing this moduli space of cubic surfaces. Okay, so next I want to in our research, actually, the both description is used. So we have to use both this GIT interpretation as well as this Billy-Brown interpretation. So this is actually quite subtle. So we have to use both description. So now let's consider the following question. So maybe this is part 2. So let's consider so this is a cubic threefold. This cubic threefold is not like a second cover or anything arising from cubic surface, but it's just a cubic threefold on its own right. So because the naive idea is the following: because this cubic threefold, the cubic surface moduli is 4-dimensional, and cubic threefold is in P4, so you can take hyperplane sections, and which is also 4-dimensional. And the natural question is to ask is that how do you compare this 4-dimensional to this like a 4-dimensional space? So by taking hyperplane sections, we have a rational map which is from the dual space to this like a both analytic and algebraic moduli space, which is I'll just add qubit bar, which is a honest projective variety. So the question is that so this is 4-dimensional, this is 4-dimensional. So suppose suppose this is like a it doesn't contract a curve, so this will suppose this is dominant. Suppose this is dominant. Dominant. What is the degree? What is, so let's give a name. Let's say it's phi. What is the degree? So this is our big motivation questions. What is the degree of this? Right. Okay, so this is a with X it's a Fermat cubic threefold, which is probably the first cubic threefold one coming to mind, because its hyperplane section is some cubic surface is very close to Fermat, and very symmetric. And so this is by Rosenberg in I think it's in around 1990. So then degree of this phi is actually just the automorphism. So by doing projective change of coordinate, and you get, of course, that's a trivial orbits of the cubic surface, which should send to the same point.
You mean the size of the group?
Oh yeah, it is a size. Yeah, it's order. It's actually something like this number. And what they prove is actually this automorphism is everything that you expect this arising from contracting many points to one point. So this is so maybe then we can ask is that what about X is general, and in the sense that you consider Fermat cubic, which is one extreme, which is has the largest symmetric, maybe almost the largest symmetric group, but you can consider the other extreme, which has no automorphism, and what is going to happen. So this is our ongoing project. We haven't completely solved the problem, but we are halfway through the solution. So so let's think about how do we transform this problem into something into a different problem. So what we consider is actually following. So we want to resolve this map. We want to resolve this map. So we want to resolve this projective space and extend this map to a regular map. And so after doing this, the degree of phi can be computed using intersection theory. So this modular space, as GRT modular space, has a divisor. This is a divisor, which parameterizing all the nodal cubic surfaces. And so you can, because this is a generic finite, and if you you pull back, you can pull back this divisor to here. So also because this is a sort of only have quotient singularity, you expect that intersection theory still works fine. So it doesn't really matter. So idea is that we transform this topological data to something like intersection theory. So we pull back using this regular map of this divisor. Well, this is become a divisor here. It will be interacting with the exception divisor, but if we consider fourfold self-intersection and divided by the fourfold self-intersection of the divisor here, and that's your honest degree. That's honest topological. So basically, we transform to this, and because this is a, remember, this is a weighted projective space 1, 2, 3, 4, 5. This is already known. So what is this a nodal divisor, and how it's the intersection number? It's already known. So it turns out that it is actually how to characterize what is a pullback. Well, you should first construct this blow up, and then describe your exception divisors, and then figure out what is pullback, and together with multiplicity on these exception divisors, and then figure out what is their mutual intersection. So we sort of transform our problem into the problem reduces to find one explicit resolution. Let's call it sigma. Two intersection numbers among those exception divisors. And also I should say that maybe this is immediate, but I should say that this is if you consider the dual variety, which parameterize the hyperplane section, which is singular. It is a hypersurface in P4 dual, and so this divisor will be mapped to this nodal divisor, because you consider general singular hyperplane section which only have a node. So this is this is not a morphism, but it's a dashed morphism. This is the one you want. So you basically you expect you putting back has some strict transform of this divisor. So your self-intersection is also among exceptional divisors and the strict transform of the dual variety. So last one is to find the pullback. Right. So are there any questions so far about the problem we are going to do and our strategy? Okay, so if there is no problem, no question, I'll just say that we are, what have we done so far is this. So we completed an explicit resolution, and where this is going to extend. And we sort of considered like a 50% of this part of intersection numbers. And we haven't got the step 3 so far. So maybe I'll just explain how this resolution is going to be constructed, and also where is the geometry is coming from. So,
Yilong, do you use any this ball quotient stuff, transcendental things, or it is purely algebraic?
It is using transcendental. So this, yeah, that's a good question. So here we actually use this is Toledo. We construct some explicit resolution, and we have to use what is so-called a Borel extension theorem, and to show that this really extends. So maybe I'll just see here. So there is a theorem of Borel extension. And say if you have a space, W is say a complex manifold. And suppose we have a map to like the ball quotient, and it's holomorphic. And suppose you have a compactification which is a simple normal crossing divisor on the boundary. So theorems claim that actually this map will extend to here. So it extend. There exists an extension holomorphic. So here is what we use that it is Bailey-Breuil, and also our construction is locally analytic, and sort of it's just natural to use this result. So in fact, I was thinking about to produce an algebraic proof, but I'm still looking for that. So let me maybe say where this theorem is used in the construction. So
and the result is for the generic or for any X? I mean, the construction of this.
In our construction is for general X.
General.
Yeah, in our construction is for general X. So maybe I'll just mention that for Rosenberg theorem for our cubic, that resolution is also described, but it's not too difficult. It's for generic cases a little bit difficult. So it's so for Rosenberg it's just a two-step reduced blow up at the points and at the street transformer lines. And for us, we consider it's not a blow up at some points or like that. It's somehow related to the stable reduction. So we have to do something base change, and then blow up and then quotient. And sort of what our blow up to describe is using weighted blow up. And this techniques is relied on the fact that we assuming that cubic threefold is general, and the singularity is no worse than ADE singularity. So it doesn't have this like elliptic singularities appear in the forma. So in our construction, so maybe I'll just say that. So first of all, let's just take our base space P4 dual. So this is a column 1 is dual variety. So generically it's only A1 singularity. So here is generically smooth. And for some coordination 2 things, and it's going to be cusp. So like a A2 singularity, and also some A1 cross A1. And for higher coordination, you have something worse. You have A3, and also some product singularity. And in the worst case, which I couldn't write on the other blackboard, but I'll say that it's just A4 and B4. So this is a coordination 1, coordination 2, coordination 3, and coordination 4. So so that's the stratification of dual varieties. So how to construct resolution of the rational map? So let's say around an A2 singularity. So suppose P in this dual variety, let's just before dual, corresponds to a hyperplane with intersection as an A2 singularity. So then you can take an analytic neighborhood of this P in the P2 dual. This is just an analytic open ball. So we can think about this as a 2-dimensional disk plus a 2-dimensional disk. So 2-dimensional disk. There are 2-dimensional disks. So it turns out that one coordinate is a trivial coordinate. The other is like a varying the deformation of A2 singularity. So in the first component, so basically delta 2 is I just identify this with like a small origin, a small open neighborhood of origin of C2, and they are corresponding at D is the discriminant divisor, which corresponding to the when you change the hyperplane, when you deform the hyperplane, and you suddenly from this hyperplane with A2 singularity to some hyperplane section with only A1 singularity along this curve, and off this curve is smooth. So that's so this picture is on the 2-dimensional slice of the dual variety. So then, this is a result of many people. It's basically Bracecorn and even very classical Schiavelli and Harishchandra and so on and so forth. Is that this is actually arising from some quotient of affine space under the wire group action, which is some finite group. So in other words, if you you can find some finite group action on the affine space whose quotient is still an affine space. So C2 to C2. So this quotient is a symmetric group of order 3, which is a wire group of A2. So this is a wire group of A2. So it turns out the benefit of this interpretation is that so this is still a C2, but if you pull back this discriminant divisor, it's actually a hyperplane arrangement where this is actually a root system of A2. So it's in this case, it's a 3-line intersecting at the origin. And in this case, this blow up is I mean, you can think about we are just want to like blow up this divisor, which the simplest case is just so blow up at origin. So we obtain an exception divisor and 3-line in this picture. So by passing this quotient on this blow up, because this exception divisor is invariant, you can do this, and you really get some two-dimensional space delta to tilde, and which is like a map to this is variational. It is some sort of weighted blow up. And this is just so again, this two-dimensional arising like from a two-dimensional slice of an open ball of a point corresponding to A2 singularities, and so this, and you will see that this 2, 3 lines, and which actually corresponds to 1 line. And this exceptional divisor has some quotient singularity. So this is the picture. So the quotient singularity doesn't really appear on this red line. So this red line you should really think about. This is the dual writing, but it's a two-dimensional slice. And so maybe this is just trying to relate what we have just talked about. It's a Borel extension. Where is Borel extension is coming from? It's here. So we want to do some like a blow up on the finite power where it is canonical. And by the way, this resolution was called wonderful blow up. So this is I'll say this is a so-called wonderful blow up. It's given by Carlson, in the 80s. So in general, it's given by wonderful blow up, which is a log resolution of hyperplane arrangement. And so this so this is going to say we have like a holomorphic map from complement of this divisor to the moduli space. Which is only rational. This is rational. But here, by this is regular. by this so-called Borel extension. And so this uses the fact that this is also a Bailey-Brill quantification. I mean, this is just demonstration of A2 singularities for A2, A3, A4, D4, and so on and so forth. They are similar, just a little bit more involved than this one blow up. It's like a successful blow up, and but that's the sort of idea, and also that's if you do the A3 blow up, you will see that how the A2 is going to appear in the picture, and so this is just going to tell. Even what we do is local analytic neighborhood, and because this this is canonical at every AD singularity, they glue together, and so you really have honest manifold appear there, which extend the extend this map to the moduli space. I think I'll stop here. Sorry for like a.
Good that you can stop recording.